Hello everyone. Now I'm going to tell you about a message queue, which is an inter-process communication. Let's begin now. Let's see what is a message queue. In computer science, message queues and mailboxes are software engineering components which are used for inter-process communication or for inter-thread communication within the same process. They use a queue for messaging, the passing of control or of content. This is a diagram which depicts how the message queue is being used to send the messages between two applications. There is a sending application here and there is a receiving application here. Both of them are communicating with each other using the message queue. The sending application will place a message which is to be sent by the destination on this queue, and the receiving application will receive it from this queue. Now let's start with the features. Okay. Now features are like message queues provide an asynchronous communication protocols, meaning that the sender and receiver of the message do not need to interact with the message queue at the same time. This means that message queues provide an asynchronous communication, means there is no need for them to interact even when the message queue that is, both of them have to be there is no need for them to interact with each other at the same time. This is what it means. Messages placed onto the queue are stored until the recipient retrieves them. Next feature is message queues. Message queues have implicit or explicit limits on the size of the data that may be transmitted in a single message and the number of messages that may remain outstanding on the queue. So these are the important features of the message queue. Now I have given just the open sources which are available in the middleware systems for these message queues. These are some of the open source choices. These help in various applications. We can use these resources and use them as a message queue tools and for communication. Next is how does this message queue works. So this is the diagram which tells that, as we seen in the earlier diagram, we have seen in the earlier diagram that, just a moment, like how this yes, see this there is a sending process, then we have a receiving process. So the sending process passes the message in the message passing module, and here is the message and the type. This is actually the queue which will be having the message along with type. This message will be having all the detail with the header. All these components will be present here. Then comes this receiving process, which will take this message from this module and then displays this message if it is required. So in this message queue, one of the application that we can see here is the reservation systems, that is like railway reservation systems, airline reservation systems. Example, like if you want to send one of the message to the user or the customer saying that the train is delayed or the flight is delayed, then we can make use of this message queue in our application, where we can communicate it to the user using this queue with the message. Now let's see the working of this message queue, which we've seen in the diagram now. Message queue is a linked list of messages stored within the kernel and identified by an identifier. A new queue is created or an existing queue opened by message get. New messages are added to the end of the queue by send, Every message has a positive long integer type field, a non-negative length, and the actual data bytes, that is to the length correspondence, all of which are specified to message send when the message is added to the queue. Then once the messages are sent and it is at the one end of the queue, they have to be received by the receiving application. How does this happen? It happens through one more uh, call, that is message receive. All processes can exchange the information through access to a common system message queue. The sending process places a message via some OS message passing module onto a queue, which can be read by another process. Each message is given an identification so that processes can select the appropriate message. Process must share a common key in order to gain access to the queue in the first place. So these are the steps which tell about how the message queue communicates between two applications which want to communicate in the inter-process communication. So all these message send, message receive, which I've been telling here, these are called as system calls. Let's see what the system calls do. So this is one of the diagram which tells about the system calls. What the system call FTOK does, it is used to generate a unique key. Then MSG this either returns the message queue identifier for a newly created message queue or returns the identifiers for a queue which exists with the same key value. Message send, data is placed onto a message queue by calling message send. Message receive, messages are retrieved from a queue. Message CTL, it performs various operations on a queue. Generally, it is used to destroy the message queue. We will see the usage of all the system calls in our program. Now, I'm going to tell you about the full description of the system calls. What are the return types, prototype, arguments, everything. Let's see what does FTOK does. Its prototype is as shown in this document here. So it is key underscore T FTOK. What is this key underscore T? It is a value of type key underscore T here. This what is the return values are? It will return this key underscore T value on success, -1 on failure. So what are the arguments? First is nothing but the path name. Next is the ID value. So this function shall return a key based on path and ID that is usable in subsequent calls to message get, SCN get, and SHM get. These are some of the system calls, SCN get, SHM get in shared memory and semaphore. So the FTOK function shall return the same key value for all paths that name the same file when called with the same ID value, and return different key values when called with the different ID values, or with the paths that name different files existing on the same file system at the same time. So in our program, how we have used this FTOK is shown here. So this is the path name and this is the ID value. So this file will be consisting of this unique ID value. Then the program which is doing this message queue communication with all system calls, message receive, message send and all, will make this key value that is, they use this key value from this file. Okay. Next, let's get into message get. Message get is of integer type. This uses this key underscore T key which we had used it in FTOK and the message flag. It returns the identifier on success and -1 on error. Now let's see what are the arguments going to tell. As I told you, the first argument is the key value. Next is the message flag. It has two values. First is IPC create. It creates the queue if it doesn't exist. Then IPCEXCL, when used with the IPC create, fail if queue already exists. Okay. Next, the description. what this message get system call will do, it takes a key as an argument and returns a descriptor of the queue with the matching key if it exists. If it does not exist, and the IPC create flag is set. That is what I said before. IPC create is used to create a new queue if it doesn't exist. It makes a new message queue with the given key and returns its descriptor. There is also an optional octal mode may be ordered into the mask, since each IPC object has permissions that are similar in functionality to file permissions on a Unix file system. So this is how this message get is used in our code. This key, whatever we have got from the FT, okay, that is written. It is ordered with this permissions, okay. Then this is flag is used to indicate that it has to be created. Now let's come to the receive system call. So receive system call has this prototype. We will see what all these arguments are. Then these arguments now will start it. This function reads a message from the queue associated with the MessageQueue identifier specified by the MessageQueue ID. The argument message P points to a user-defined buffer that must contain first a field of type longint that will specify the type of the message. So it is talking about this one. And then a data portion that will hold the data bytes of the message. The argument MessageSend specifies the size in bytes of a text. Let's see, the argument message type specifies the type of the message requested as follows. So message type is 0, the first message on the queue is received. The message type is greater than 0, first message of the type MSGTYP is received. MSGTYP is less than 0, then the first message of the lowest type, that is less than or equal to the absolute value of MSGTYP, is received. Let's see the description. Why this message receive is used. It is used to receive a message from a given queue descriptor. See, we send it at one application which has to be received at the other application. So it is used to receive message from a given queue descriptor. The caller process must have read permissions for the queue. It is of two types. Blocking receive puts the child to sleep. If it cannot find a requested message, it sleeps till another message is posted in the queue and then wakes up to check again. Non-blocking receive returns immediately to the caller mentioning that it failed. Now in this code we have used message receivers like this. We have a message ID which is generated there, and we are using a structure actually which is of type message, and then we have the size of the structure. Then we are using as I have told here, its prototype is having two more arguments at the end, which are the message type and the message flag. So it is message type is given here 0 and all, and this message size. Okay, this is message size and message type. Message CTL prototype is shown here. It returns 0 on success, -1 on error. Arguments is first argument is the message ID, second argument is a command to be used along with this system call. So this second argument is having all these values. These are the commands which are used. If this command is, what is going to happen? It retrieves the MessageQueue ID underscore DS structure for a queue and stores it in the address of the buffer argument. This sets the value of the IPC per member of MessageQueue ID underscore DS structure for a queue, takes the values from the buffer argument. So IPC RMID, it removes the queue from the count. So the CTL, why it is used, we will see it here in the description. It is used to change the message queue parameters like the owner. Most importantly, it is used to delete the message queue. So when two processes are communicating with each other, once the message queue is done with its job, it is to be deleted. So mainly this CTL is used for that purpose. So this IPC RMID flag can be used for this purpose in this message queue system call. A message queue can be deleted only by its creator, owner, or the super user. So how do we use this CTL in our code is like this. Then finally we have message send system call. It is of this prototype. It returns 0 on success, -1 on error. Then the arguments tell me that the first argument to message send is our queue identifier returned by a previous call to message get. Second argument tells it is a pointer to our redeclared and loaded message buffer. The message is Z argument contains the size of the message in bytes excluding the length of the message type. This flag argument can be set to 0 or it can be IPC no wait. If the message queue is full, then the message is not returned to the queue and control is returned to the calling process. If not specified, then the calling process will block until the message can be written. Let's see what does this do. So when we have this system call, we can begin performing operations like to deliver a message to the queue, where mainly this system call is used. So in our code we have used it in this manner. Let us take a problem statement now and use these system calls for message passing. In this, that is for message queue. In this example, we are creating a writer and the reader processes. Writer process takes the input from the user and sends the message. Reader process will read and the data sent by the writer process by creating the new message queue. So see, this is how reader and writer will communicate. First, the writer will use FTOK. It will generate a key. Message get will use this FTOK, take that key value, and then it will write the message, and then it will send this. At the reader, again it does message get, where another queue will be created with the same key value so that both of them will communicate with each other. Then it will call the system called receive and receives that message, displays that message, and finally the queue will be deleted by CTL. This is what we are doing it in our program. Let's see some of the header files which I have included in my program, that is in our program. See what does this header file do. It is used by 3 mechanisms for interprocess communication: messages, semaphores, and shared memory. All use a common structure type IPC perm to pass information used in determining permission to perform an IPC operation. IPC create definition is defined by this header. So we are using IPC create. So this is done here in this header file. Another header file is this message.h. This has the following as declared as functions and may also be defined as macros. Function prototypes must be provided for use with an ISOC compiler. So these are some of the methods in this in this header file. Now let's start with the code. What does the writer process do? So this is the structure of the message queue that I'm using. It is named as message. Okay. Next is the main. We have, see here, FTOK is used to generate the unique key. Then comes the message get. As we have seen already in the diagram, first FTOK is used to generate the key. This key only will be used by message get. Okay. This creates a message queue and returns the identifier. So what does this 0666 is used? It means that all users can read and write but cannot execute. Then what they do, they print this data. Means it will ask the user for the input, what data is to be taken in. User can give the input here. Okay. The gets function is used to scan a line of text from the standard input device. Then the message send is used to send the message. Finally, whatever the message will be sent, that will be displayed here. Now comes the reader process. This is again using the same structure. Okay. This same structure, again it is using the same key value, identifier from this file. this key only has to be again used to generate one more queue with these permissions. Then it has to receive the message. The message received has to be taking an argument of this structure. Okay, once it is received, the data received will be printed here. Finally, it has to destroy the message queue with this system call. This is all about the programs. Next, we will see how the output looks like. See, so this is the output here. It asks for write the data. We say hi and welcome. So that this hi and welcome message will be sent. Okay. This is the writer process. In the same way, reader process will also be there. The reader process will say, if I execute it, it will say the data received is hi and welcome. This is how it is done. A message is sent by the writer and the reader is going to read it and print it. So some of the advantages and disadvantages of MessageQueue. Better performance. So MessageQueues enable asynchronous communication, which means that the endpoints that are producing and consuming the messages interact with the queue, not with each other. Producers can add requests to the queue without waiting for them to be processed. Consumers process messages only when they are available. No component in the system is ever stalled waiting for another, optimizing the data flow. So first is the better performance. Now it is increased reliability. Queues make your data persistent and reduce the errors that happen when different parts of your system go offline. So by separating different components with the message queues, you create more fault tolerance. If one part of the system is ever unreachable, the other can still continue to interact with the queue. So the queue itself can also be mirrored for even more availability. Granular scalability. Message queues make it possible to scale precisely where you need to. When workloads peak, multiple instances of your application can all add requests to the queue without risk of collision. As your queues get longer with these incoming requests, you can distribute the workload across a fleet of consumers, producers, consumers, and the queue itself can all grow and shrink on demand. So these are some of the disadvantages. Now, some of the references I have made for this document. So all the data which contains in this document are the references being made from these websites. Thank you.